Discuss the continuity of the function f of x equals to x squared plus 1 divided by x squared minus 3x plus 2. A rational function p of x divided by q of x, where p of x and q of x are polynomials, is continuous everywhere except at the points where q of x is equal to 0. Rewriting the given rational function in fully factored form. In this case, the numerator cannot be factored, but the denominator can be factored. The numerator stays the same, x squared plus 1, and the denominator becomes x minus 2 times x minus 1. So this function is discontinuous at points where the denominator becomes 0. That is, when x minus 2 times x minus 1 is equal to 0. This happens at x equals to 2 and x equals to 1. So these are the points where the function is discontinuous and is continuous everywhere else. Discuss the discontinuity of the function f of x equals to 2x divided by x squared minus 2x minus 8. The rational function f of x equals to 2x divided by x squared minus 2x minus 8 is discontinuous at the points where the denominator becomes 0. Writing the denominator in fully factored form, we have f of x equals to 2x divided by x minus 4 times x plus 2. This function is discontinuous when x minus 4 times x plus 2 becomes 0. This happens at x equals to 4 and at x equals to negative 2. Determine where the given piecewise function is discontinuous. f of x equals to 1 for x less than 1 is equal to x minus 2 squared, 1 less than or equal to x less than or equal to 4, and is equal to 5 for x greater than 4. To determine the continuity of a piecewise function, the limits at points where the formula of the function changes must be investigated. In this case, the formula of the function changes at x equals to 1, that's case 1, and case 2 at x equals to 4. A function f of x is continuous at a point x equals to c if the limit of f of x as x tends to c is equal to f of c, meaning the limit of the function f of x must exist as x approaches c, and it must be equal to the value of the function at c. Let us consider the limit of the function at x equals to 1. Limit as x approaches 1 from the negative side of the function is the formula for which x is less than 1. In this case, it is equal to 1. So limit of the constant 1 is equal to 1. Limit of the function as x approaches 1 from the positive side is the formula for which x is greater than 1, which is x minus 2 squared. And the limit of this function is 1. Since the limit as x approaches 1 from the negative side is equal to the limit as x approaches 1 from the positive side, the limit of this function f of x exists. To show that the function is continuous at x equals to 1, we must show limit as x approaches 1 of the function f of x is equal to the value of the function at x equals to 1. Limit of f of x as x tends to 1 is equal to 1, which is equal to f of 1. And f of 1 is f of x at x equals to 1, which corresponds to the formula x minus 2 squared. Substituting x equals to 1, we obtain the value equals to 1. The limit and the value of the function at x equals to 1 are equal. Therefore, the function is continuous at x equals to 1. Case 2, x equals to 4. Limit as x goes to 4 from the negative side of the function f of x is the piece that satisfies the condition x less than 4, since we are approaching 4 from the negative side for which x is less than 4. Applying limit, we obtain the value equals to 4. Similarly, limit as x approaches 4 from the positive side of the function satisfying this condition, x greater than 4, is 5. And the limit of the constant is constant. Since the left and right limits of the function as x approaches 4 are unequal, the limit does not exist, and the function is discontinuous at x equals to 4. We can verify this by graphing the piecewise function as shown in this graph. F of x equals to 1 is the horizontal line passing through the point 1 for values x strictly less than 1. Therefore, you see a hole here. And f of x equals to x minus 2 squared is the graph of the function f of x equals to x squared shifted 2 units to the right for the values x between 1 and 4, both inclusive. And f of x equals to 5 is a horizontal line for the values x strictly greater than 4. Observe from the graph, we have a discontinuity of the function at x equals to 4. Find the value of constant k such that the given function is continuous. F of x equals to x squared plus k for x less than or equal to 2, and f of x equals to kx minus 3 for x greater than 2. Since the given piecewise function is continuous everywhere, each piece of the function must approach the same value at x equals to 2. We have x squared plus k equals to kx minus 3 at x equals to 2. Substituting x equals to 2, we obtain 4 plus k equals to 2 times k minus 3. Simplifying, we obtain k equals to 7.